Right now, the blood pumping inside your chest is moving through your arteries using the exact same physical principles that keep a 400,000-pound airplane in the sky.
Yeah, and it's actually the exact same physics that dictate how a pitcher throws a curveball, which is pretty wild to think about.
It really is. So, welcome to today's deep dive. We are unpacking a custom presentation today titled Part 06B Fluids in Motion Physics for Biological Systems.
Right, and the mission for this deep dive is, well, it's pretty straightforward.
Exactly. If you're naturally curious, or maybe you're prepping for a tough class, you want to understand how the world actually works without, drowning in academic jargon.
We want to simplify these core fluid mechanics for you, especially if you don't have a background in advanced physics.
Because we're going to prove that physics isn't just abstract math meant for a chalkboard. It's really the invisible architect of your entire cardiovascular system.
I mean, biology and physics are often treated as two separate things, right?
Yeah.
But biological systems are completely bound by the physical world.
A living body cannot just violate the laws of thermodynamics or fluid dynamics.
Exactly. You can't truly grasp how the human body functions until you understand the mechanical rules it's essentially forced to play by.
So let's open up this presentation and look at the first slide. It actually sets the stage perfectly with this striking geometric artwork of blood vessels.
It does. And it starts with a seemingly basic question, which is what actually is a fluid?
Right, because establishing definitions is always the necessary first step.
Yeah, in physics, a fluid isn't just a liquid like water or blood. It also encompasses gases, like the air that's filling your lungs right now.
The presentation defines a fluid by its physical behavior, right? It says it continuously deforms under shear stress.
That's the one. And we should probably pause on shear stress, because that is one of those terms that gets thrown around a lot in physics classes.
Yeah, what does it actually mean for a fluid to deform under it?
Well, imagine a really thick deck of playing cards resting on a table. If you press your hand flat on the top card and just push horizontally, that top card slides forward.
Okay, I can picture that.
And as it slides, friction pulls the second card along a little bit, and that one pulls the third card, and so on. That lateral force you applied is shear stress.
So if you apply that same force to like a solid block of wood, the wood just resists it. It holds its shape completely.
Right, but if you apply that lateral force to a fluid, it has absolutely no structural resistance to it. The layers of the fluid just continuously slide past one another.
It yields.
Exactly, it yields, it flows. A solid fights back, but a fluid just continuously yields to whatever force is applied.
So to map out how these yielding substances move through the incredibly complex branching geometry of the human body, we have to establish the foundational rules.
Yes. Before we can understand how fluids navigate that biological maze, we really need to know how they interact with the walls of the pipes they travel through.
So let's look at how fluids behave when they actually touch the inner lining of our blood vessels.
Great. I'm moving to the slide on the no-slip condition and ideal fluids now.
The no-slip condition. That sounds a bit intense.
It's a deeply counterintuitive reality of fluid dynamics, honestly. It states that any fluid in direct contact with a solid surface has zero velocity relative to that surface.
Wait, meaning the fluid is completely stopped? Like it isn't moving forward at all?
Not at all. Think about the microscopic boundary where your blood meets the artery wall. The physical molecules of the fluid get caught in the microscopic roughness of that solid surface.
Okay.
There are also intermolecular attractive forces at play there. So because of this, the outermost layer of blood is essentially glued to the inner wall of your artery.
It's totally stationary.
Yeah. And then, returning to our deck of cards analogy, that stationary layer exerts a tiny bit of friction on the next layer inward, which slows it down.
And then the layer inside that moves a tiny bit faster and the next a bit faster.
Exactly. You create this speed gradient until you reach the dead center of the vessel, where the fluid is furthest away from the walls and moving at its absolute maximum speed.
Okay, let's unpack this with a visual because I think it helps.
Yeah,
It's like a massive crowd of people trying to walk down a really busy hallway.
I like this.
The people right against the walls stop to look at their phones, right? So they have zero velocity. They're just leaning against the
All
drywall.
right, the no-slip folks.
Yeah, and the people walking just past them are forced to shuffle slowly, just squeeze by.
But the people right in the middle of the hallway, away from the walls and the phone watchers, they're just rushing straight through at top speed.
Exactly, and the math bears it out perfectly right. The friction from the wall propagates inward, just dragging on the fluid.
It does. However, if an engineer or a biologist tried to calculate the exact math of every single friction point in every microscopic branch of the circulatory system simultaneously.
It would be impossible.
Yeah, the math would be totally unsolvable. It would be a chaotic system.
Yeah.
So to get around this without overwhelming the math, the presentation notes that we simplify things for our initial models.
We pretend we are dealing with ideal fluids.
Right. We establish baseline rules in a perfect world before we introduce the messy reality of the human body.
So, what exactly qualifies as an ideal fluid for these students?
We make two major assumptions here. First, the fluid is incompressible, meaning you cannot squeeze its mass into a smaller volume no matter how much pressure you apply.
Okay, makes sense. And the second?
Second, we assume it is inviscid. That means it has zero internal friction or zero viscosity. We just pretend the layers don't drag on each other at all.
Even though real blood is obviously highly viscous and super messy.
Exactly. But by temporarily stripping away that internal friction, we can just isolate the core mechanics of how flow rate and pressure work.
So, we know how an ideal fluid behaves in a perfect straight pipe. But our cardiovascular system isn't built with straight pipes.
Far from it. Arteries branch out, they widen, and sometimes dangerously they narrow.
Which leads us to what happens during those changes. Moving to the next slide on the continuity equation.
Here we see the formula A1 times V1 equals A2 times V2. This is the continuity equation.
And this is basically a mathematical expression of the conservation of mass, right?
That's it, exactly. If our ideal fluid is incompressible, then whatever volume of fluid flows into a pipe absolutely must flow out of that pipe.
The volume flow rate just has to remain perfectly constant throughout the entire system, regardless of how the vessel changes shape.
Right. So the A in that equation stands for the cross-sectional area of the vessel, and the V is the velocity of the fluid.
Because multiplying the area by the velocity must always equal the exact same constant number, those two variables are inversely proportional.
Yes. So if the area goes down because the pipe gets smaller, the velocity of the fluid simply must go up to compensate.
Wait, I have to push back on this for a second because my everyday intuition says the exact opposite.
Most people's does.
If a blood vessel gets narrow, you are creating a bottleneck. Shouldn't it be harder for the blood to get through? Why wouldn't a bottleneck slow the blood down?
It is such a common misconception, but we have to look at the physical mechanics of mass conservation. Think of it like a factory quota.
Okay, a quota.
Let's say 1 liter of blood enters a wide section of an artery every single minute. Because the fluid cannot be compressed into a smaller space, 1 liter of blood absolutely must exit the other side every single minute.
It can't just disappear.
Right. So if it suddenly hits a bottleneck, a tiny narrow gap, the fluid can't just pile up like cars in traffic. To get that exact same physical volume of blood through a much smaller opening in the exact same amount of time, it has to rush.
The molecules are basically forced to accelerate to make the quota.
Exactly. They have to move faster.
That makes total sense when you put it in terms of a quota. It's like the garden hose effect, right?
Oh, perfect example.
When you're watering the lawn and you want the water to shoot further across the yard, you just stick your thumb over half the nozzle.
Right. You decrease the area of the opening so the water's velocity skyrockets.
And biology exploits this mechanism constantly, doesn't it?
Constantly. Arteries are incredibly dynamic structures. They're surrounded by smooth muscle, so they constantly constrict and dilate, intentionally changing their cross-sectional area.
So they can regulate the flow speed and distribute blood exactly where the body needs it at any given moment.
Precisely. But that sudden increase in speed through a narrow gap comes with a hidden physical cost.
And this leads us to one of the most important and honestly dangerous principles in hemodynamics. Let's go to the next slide covering Bernoulli's principle.
Yes. When it comes to understanding fluid flow in the body, this is arguably the most vital concept in the entire presentation.
Bernoulli's principle. I feel like that name usually makes students tense up.
It does sound intimidating, but at its core, it's just a beautiful concept of balance and energy conservation.
Okay, so what is the actual rule here?
Bernoulli's principle states that along a steady streamline of fluid, the total mechanical energy of that fluid remains perfectly constant.
And that total energy is a combination of three things, right?
Right. The static pressure exerted by the fluid, the kinetic energy, which is just the energy of its physical motion, and potential energy, which relates to gravity and its height.
So pressure plus kinetic energy plus potential energy always equals a constant number. It's just a closed system.
Exactly. Now, for our biological model, if we assume a blood vessel is horizontal, the height isn't changing. So we can just factor out potential energy completely.
Which means we are left with a direct zero-sum battle between lateral pressure and kinetic energy.
That is the big aha moment.
Here's where it gets really interesting. If the total energy is fixed, we can think of it like a financial budget.
Okay, let's hear the budget analogy.
Let's say a certain volume of fluid has a fixed energy budget of exactly $100.
Right.
It has to spend that money on either moving forward down the pipe, which is kinetic energy, or pushing outward against the walls of the vessel, which is pressure.
Tracking so far.
If the fluid suddenly hits a narrow patch, as the continuity equation just proved, it is forced to accelerate. So it might have to spend, say, $80 of its budget just on moving really fast.
Which means it only have $20 left over to push outward against the walls.
Exactly. The trade-off is unavoidable. As fluid speed goes up, its internal lateral pressure simply must drop.
It's a perfect way to explain it. And to understand why this happens physically, we just have to look at the molecules.
What are the molecules doing?
Well, pressure is simply the force of fluid molecules bouncing against the walls of their container. If fluid is moving slowly, the molecules have plenty of time and random energy to ping-pong laterally against the walls.
Lots of bouncing means high lateral pressure.
Right. But if you force that crowd of molecules to sprint forward as fast as possible through a narrow gap, all their directional energy is focused straight ahead.
They aren't bouncing side to side against the walls nearly as much. Less lateral bouncing means lower lateral pressure.
Exactly. And this molecular trade-off is not just physics trivia. It has huge clinical applications.
Yeah, the slide on biological application, blood pressure, and flow shows a three-stage diagram of an artery that illustrates why this is literally a matter of life and death.
This is where we see Bernoulli's principle operating clinically. The diagram shows arterial stenosis, which is the abnormal narrowing of a blood vessel.
Usually due to a buildup of plaque, right?
Yes. In stage 1, you have a wide, healthy artery. The blood moves at a normal, relatively slow pace, which means it has a high budget for lateral pressure.
That pressure pushes outward, keeping the flexible vessel nicely inflated. But then in stage 2, the blood encounters the plaque. The artery narrows.
And following the continuity equation, the blood is forced to accelerate rapidly just to get through the narrow gap. The kinetic energy spikes.
The budget is spent on speed. All that directional energy is focused forward.
Because the blood is moving so incredibly fast, the lateral pressure pushing outward against the artery walls drops significantly.
Which creates stage 3, a highly dangerous pressure differential.
Right. The external pressure from the tissue surrounding the blood vessel might now be stronger than the internal pressure pushing out.
Which creates a severe risk that the vessel wall could completely collapse inward, entirely cutting off blood flow.
It's a massive clinical risk.
It is wild that a clogged pipe wouldn't have high pressure right at the clog. Because the speed is so high, it effectively creates a low pressure zone that sucks the walls inward.
It's very counterintuitive until you see the math. I want to skip ahead past the medical manometer slide for a second.
Okay, skipping ahead to the airplane and the baseball slides.
Yes, because this exact same principle powers modern transportation and sports, and it really helps solidify the concept.
I mentioned airplanes in the very beginning. How does blood vessel physics make a plane fly?
Well, look at the cross-section of an airplane wing. It's highly curved on the top and relatively flat on the bottom.
Right, the classic wing shape.
As the plane's engines push it forward through the fluid of the air traveling over that curved top surface has a longer physical distance to travel to reach the back of the wing.
Compared to the air going under the flat bottom.
Exactly. To keep up, the air on top has to accelerate. It moves faster. And faster air, as we know from Bernoulli, means lower lateral pressure pressing down on the wing.
Budget spent on speed, so pressure drops.
The pressure pushing down on top of the wing is now lower than the slower moving high pressure air underneath the wing.
And high pressure always seeks to move into low pressure areas, so the air underneath pushes upward.
That upward force is lift. That pressure differential is what carries a massive plane into the sky.
That is so cool. And the Magnus effect in baseball operates on those similar pressure zones, right?
It does. When a pitcher throws a curveball, they put a fierce, rapid spin on the ball. The seams of the spinning baseball literally drag a boundary layer of air around with it.
Okay, I'm picturing it.
On one side of the spinning ball, that drag air goes in the exact same direction as the oncoming wind, accelerating the airflow on that side.
But on the opposite side, the spinning air fights the oncoming wind, slowing it down.
Right. Fast air on one side equals low pressure. Slow air on the other side equals high pressure.
And the high pressure naturally pushes the ball toward the low pressure zone, and the ball physically curves in midair.
It's just a brilliant demonstration of asymmetrical pressure differentials. But, shifting back to the human body, we need to consider forces that operate on an even smaller microscopic scale.
Yeah, having explored pressure and speed, we need to shift from the flow of fluids to the incredible forces happening at their surfaces.
Right, because we haven't discussed the unique physical forces acting at their borders.
Let's look at the next slide, focusing on surface tension and the lungs.
At a molecular level, liquid molecules are highly attracted to one another. Inside a puddle of water, a single molecule is pulled equally in every direction by all the neighbors surrounding it.
It's perfectly balanced.
It is. But at the surface, where the water meets the air, the water molecules only have neighbors beside them and below them.
Because there's nothing pulling them from above.
Exactly. So they pull inward and sideways much more tightly, creating this tense, invisible boundary layer that constantly tries to minimize its total surface area.
This is why a falling droplet of water naturally forms a perfect sphere, isn't it?
Yes, a sphere is the geometric shape, with the absolute minimum surface area for any given volume.
The water molecules are essentially hugging each other as tightly as possible to avoid interacting with the air.
That cohesive force, combined with adhesion, which is when the fluid molecules are attracted to the solid surface of whatever container they are in, creates capillary action.
Capillary action. That's the phenomenon where fluid climbs upward in very narrow tubes, entirely defying gravity.
It's the exact mechanism that allows giant redwood trees to pull water hundreds of feet into the canopy without a mechanical pump.
And it's essential for driving microcirculation in our smallest capillaries, too. But the presentation highlights a massive biological consequence of surface tension, specifically inside our lungs.
Yes, let's look at the alveoli slide for this.
Your lungs are packed with millions of tiny balloon-like air sacs called alveoli, right?
Right, this is where oxygen enters the blood. The inner lining of these alveoli is coated in a very thin layer of fluid.
Now, because of the surface tension of that fluid, it constantly wants to pull together and minimize its surface area.
And the surface tension in that fluid is so incredibly strong that every time you exhaled and the alveoli got smaller, the tension would just pull the walls inward and snap them completely shut.
The tiny balloons would just collapse.
They would.
So wait, without some kind of biological intervention, taking a single breath would require an enormous physical effort.
It would be exhausting.
You would have to forcefully rip open millions of tiny, wet, collapsed balloons in your chest just to pull air in.
And mathematically, it would be impossible to sustain for very long. The physical effort would cause respiratory failure,
Wow.
but biology evolved a really sophisticated chemical solution, which is surfactant.
Surfactant. I've heard that described as basically biological dish soap.
That's a great analogy, actually.
Because if you drop liquid dish soap into a bowl of water, it instantly breaks the surface tension. The water molecules just stop pulling on each other. So is our body basically making soap in our lungs?
Functionally, the result is very similar, but the mechanical reality is a bit more complex. The body secretes a specialized mixture of lipids and proteins.
Okay.
Water molecules love to bond with each other through really strong hydrogen bonds. Surfactant molecules are amphiphilic, meaning one end of the molecule loves water and the other end hates water.
So when they released into the alveoli, what happens?
They wedge themselves between the water molecules. They physically push the water molecules apart, disrupting those strong hydrogen bonds and drastically weakening the cohesive pull.
Which dramatically lowers the surface tension.
Exactly, allowing the alveoli to remain open and compliant, making the act of breathing basically effortless.
It is wild that our survival comes down to lipids wedging themselves between water molecules so they stop hugging each other so tightly.
It's elegant biology.
Which brings us to our final major topic. Up until now, we assumed our fluids were ideal, meaning they had no internal friction, just to make understanding all this a bit easier.
But now we have to drop that assumption.
Right, we have to face the messy reality of biology. Because human blood is definitely not an ideal fluid.
It is absolutely not. Moving to the final instructional slides on viscosity and laminar versus turbulent flow.
So how do we define viscosity for real fluids?
We define viscosity, denoted by the Greek letter eta, as a fluid's literal resistance to flow. It's the measure of internal fluid friction.
The classic example is honey versus water,
Yeah.
right?
Yes, honey has a very high viscosity. It pours slowly because its internal layers heavily resist sliding past one another. Water obviously has very low viscosity.
The slide actually references Newton's law of viscosity here.
It does. It mathematically links the shear stress we discussed earlier to the rate of strain. It maps exactly how fast a fluid will deform based on how thick it is and how much force is applied.
So, what are the biological stakes of viscosity? Does the thickness of our blood actually fluctuate?
Oh, it fluctuates significantly. Blood viscosity is highly dependent on a clinical metric known as hematocrit, which is the percentage of red blood cells occupying your blood volume.
It's also sensitive to temperature, too, right?
Yes, if you have a condition like polycythemia, your body overproduces red blood cells, causing your hematocrit to spike.
That makes the blood much thicker. It moves closer to the consistency of honey than water.
Right. And forcing a highly viscous fluid through a massive circulatory system requires vastly more mechanical effort than pushing a thin fluid.
So, a higher hematocrit results in a significantly overworked heart muscle.
Exactly. The heart has to pump much harder just to maintain basic circulation.
That internal friction dictates not just how hard the heart works, but how the fluid physically moves. Which brings us to the slide comparing laminar and turbulent flow.
When we look at small, healthy blood vessels, we see laminar flow. The slide uses a nice green color scheme to indicate healthy, normal function here.
Okay, so what does laminar flow look like?
It's smooth, highly layered motion. The fluid particles follow perfectly parallel streamlines, sliding past each other cleanly with very little kinetic energy lost to internal friction.
We can visualize laminar flow like a highly organized marching band. Everyone is in their designated lane, moving efficiently down the street at the exact same pace.
I love that visual.
Nobody's bumping into anyone else, and all the energy is directed straight forward.
Conversely, we have turbulent flow, which is marked in red for danger on the slide. This is a state of chaotic swirling eddies.
The fluid particles are no longer parallel.
Right, they are crashing into each other, crossing streams, and dissipating a massive amount of mechanical energy.
So, if laminar flow is a disciplined marching band, turbulent flow is basically a chaotic mosh pit.
Yes, energy is being wasted entirely on crashing into your neighbors instead of actually moving down the street.
That makes so much sense.
And the marching band versus mosh pit visual applies perfectly to another characteristic of turbulence, which is sound.
The sound.
Yeah, marching band is organized, but a mosh pit is loud. The presentation emphasizes that turbulent flow in a pipe produces literal, audible acoustic energy.
Wait, like doctors listening to your heart through a stethoscope?
Yes, but it goes further than just the heartbeat. When a doctor uses a stethoscope and hears a heart murmur or a bruit in an artery,
Hold on, I need to stop you there. A brute. What exactly is a brute?
it's a medical term derived from the French word for noise. A bruit is the actual whooshing sound that blood makes when it rushes past an obstruction.
Oh, wow.
Yeah, if you have a healthy artery with smooth laminar flow, it's generally silent. But if blood hits a jagged piece of arterial plaque, it tumbles into chaos.
It becomes turbulent.
Exactly, and that turbulence physically vibrates the surrounding tissues. The doctor is directly listening to the acoustic noise of mosh pit blood flow.
So the plaque triggers the chaos, and you can literally hear it.
You can. And physicists and engineers can actually predict exactly when this transition from smooth to chaotic flow will occur using a dimensionless metric called the Reynolds number.
The Reynolds number, what does that calculate?
It calculates the ratio of inertial forces, the speed pushing the fluid forward against viscous forces, which is the stickiness holding it together.
The slide shows that if the Reynolds number stays below 2000, the viscous forces are strong enough to keep the flow smooth and laminar.
Right. But if the speed increases and pushes that number past 4,000, the fluid completely breaks apart into turbulence.
It's a mathematical tipping point.
It is. In biological systems, crossing that threshold into turbulence almost always signals pathology, whether it's an obstructed artery, a failing heart valve, or a dangerous aneurysm.
This has been absolutely fascinating. Let's pull up the final conclusion slide. We have covered an immense amount of ground today.
We really have.
Our mission was to prove that fluid mechanics isn't just theory, and I think the evidence is totally overwhelming.
Agreed.
The continuity equation ensures that mass is strictly conserved, forcing our blood to speed up when vessels narrow. Bernoulli's principle forces a physical trade-off between speed and lateral pressure, warning us of those dangerous vessel collapses caused by plaque.
Right, and we explored the powerful cohesive forces of surface tension.
And how our lungs deploy biological lipids to break those bonds so we can actually breathe.
Plus, We saw how the viscosity of our blood determines whether it flows silently like a marching band or loudly and chaotically like a mosh pit.
Exactly. So, what does this all mean?
Well, the final note on this presentation perfectly encapsulates the science, I think. It reads, Fluid dynamics is the invisible architect of cardiovascular health, respiration, and cellular transport. Physics is not abstract, it is alive in every heartbeat.
Such a great way to put it. Before you go, though, I want to leave you with one final thought experiment to mull over.
Oh, I love these.
We just spent this entire deep dive establishing the precise rules of fluid dynamics here on Earth. Our cardiovascular system, our capillary action, our internal pressure drops, and our heart's ability to pump viscous blood are all perfectly calibrated to fight Earth's specific gravity.
That's very true.
So, based on the mechanics we've explored today, what exactly happens to a human's internal fluid dynamics when they float in zero gravity on a 6-month trip to Mars? Keep exploring, keep asking questions, and we'll catch you on the next deep dive.